Welcome. This is Mr. Tompkins' Physics 1 class, and this is going to be my lecture over projectile motion. To start off, let's just go ahead and talk about a little bit about what projectile motion is. Projectile motion is motion that combines both vertical and horizontal movement. More specifically, it's where we have an acceleration in the vertical component of our motion with a constant velocity in our horizontal portion of our movement. And we're actually going to analyze the video to verify that that's what is happening in projectile motion. So let's go ahead and start. And if I look here, let's go to the first video here. The experimental analysis of an object undergoing projectile motion. So we'll go ahead and start this. And it's just a YouTube video that I put together, and I've analyzed the video. And he throws the ball, and the dots show the outline of where the ball was. Now, using this outline in Logger Pro, I was actually able to analyze the video and figure out some things that are going on with it. So here's the graphs that I got. This is my position versus time graphs for both the X portion of the motion and the Y portion of the motion. The red dots here are my X portions, and the blue dots are my Y component, or the Y portion of the position versus time graph. The linear xt graph that we have implies that there is a constant velocity in the X direction. That being said, the slope of a position versus time graph is also going to be called the speed of the object, or the velocity of the object. In this case, I went ahead and did a linear fit, and it is a line, and it has a slope of 3.038 meters per second. So that means the horizontal velocity of my ball is 3.038 meters per second. Now we can verify that when we look at the velocity time graph later on to say that that is actually the speed. The curved blue dots here, which show my position of my Y position versus time, implies that there is a constant velocity. And we'll see that whenever I go over here to the velocity time graph. So let's go ahead and move over to the velocity time graphs. And the linear graphs tell me that the velocity is changing constantly. So if I look at my blue, which is my Y velocity, my velocity in the vertical direction, it is somewhat of a straight linear line, it's a linear function. And whenever I did a trend line or a line of best fit, the slope of that line was negative 9.847. In this case, that's actually fairly close to what the accepted value for the acceleration of gravity, because that is what is causing the object to accelerate downward, is the fact that we have gravity pulling on the object. And we usually accept it as negative 9.81, but if you look at my error here, it's plus or minus 0.09, and so that would get me within that range, and it's very acceptable. Now, I said on the position versus time graph of my X velocity that if I looked at the trend line of my velocity in the X direction graph, it would tell me exactly what the velocity was. And so I went ahead and did a linear fit on it. And if I look here, what this is telling me is my y-intercept, which is where my velocity is at the beginning and where it's going to end at the end because the slope is almost zero, is 3.04, which is very close to that. I believe it's 3.03 that we had on the other graph. So that's just re-verifying that that slope is also the speed. And then the linear line, the linear negative slope that I have for the y velocity graph shows me that is a constant acceleration, because the slope of a velocity time graph is also called the acceleration. And I've already told you what that number was. So let's say, what does this mean for the overall motion of the ball as it's traveling through two-dimensional space? Well, the constant velocity in the x direction will remain the same throughout the whole motion. So that's what the velocity in the x direction vector would look like. It would just be an arrow pointed to the right, because that's the direction the ball is moving horizontally, and it is the same size throughout the entire motion. So the velocity in the x direction does not change. There is no acceleration, or acceleration equals zero. What is changing is that there is this acceleration in the vertical component, or the y component of my motion. And so at first, the velocity in the y direction is a vector that points up, and let's say that this vector is 3 units tall. And as it goes up, the next vector might only be 2 units tall. And then the third vector is going to be only 1 unit tall. And then at the very top, you're not going to have any kind of vertical velocity because as the ball goes up, it actually stops in midair before it comes down. You can't actually go one direction and then start going the other direction without stopping there. And as it comes back down, because the acceleration is downward, well, then in this position, I now have a downward velocity, Vy, pointed downward. And it's actually going to be going down 2 units, and then down 3 units, and then down 4 units. So that is what is happening to the vectors. The velocity in the x direction stays constant, but my y velocity changes. And that's why the apparentness of the ball, that as it goes up, it starts fast, and then it slows down at the top, and then it gets faster as it comes back down, is because the y velocity is accelerating downward. So let's say, what does that do for us? Well, we can actually start talking about the two-dimensional velocity, or and get how fast the ball is actually going by looking at the two components. So I know that there's a velocity in the x direction and it stays constant. And then there's also going to be this velocity in the y direction. And so we're going to do some vector addition, and we're going to add these two together. So we don't need the picture, so I went ahead and got rid of this. And this is what the two vectors look like on a free body diagram. And so to do the vector addition, well, it's called the head-to-tail method. So I went ahead and slid over my velocity versus y vector to the head of my velocity in the x direction vector. And then whenever I add these two together and I connect the tail of the empty tail to the empty head, I get what's called the resultant, which ends up being my actual velocity of the ball. Now, the way that I figure this out is I use, in number-wise, is I use the Pythagorean theorem, which is a squared plus b squared equals c squared. This is a 90-degree triangle, but in this case, it's going to be our velocity in the x direction squared plus the velocity in the y direction squared, and that's going to equal our overall velocity. All right, and now we know how to get to the two-dimensional velocity from both the x component and the y component of the velocity. So let's talk about how we go the other way, because when we start working word problems, they're going to tell us what the velocity is, and they're going to give us some angle that has to do with the horizontal or vertical. And that's very important that we read these angles and we put them on there correctly. So this is my velocity vector in blue, and it is showing you that there's an angle theta between the blue vector and the horizontal. Okay, in order to analyze two-dimensional motion, we usually break it down into its x and y components. So just like before when we had the x and y components, which look like this, and we got a resultant from it, now we're going to take the resultant and we're going to break it down into our x and y components. So the x component looks like this. It is a vector that shoots from the tail of our original vector straight horizontal until it lines up with the head. And that's the velocity in the x direction. The next vector, or my velocity in the y vector, looks like this. And this one starts at the horizontal, or where the head of the velocity in the x direction vector is, and shoots up to the head of our actual velocity vector. Now, the way that we solve for all of these numbers is we have to do some trig. And we start that with the three basic trig functions. We'll use cosine theta to figure out our velocity in the x direction. And we'll use sine theta to figure out our velocity in the y direction. And you have to rearrange these. Usually you're given this velocity vector here, and all you do is you multiply that to the cosine of the angle, and that'll give you your velocity in the x direction. Now, if we are given the components and we want to figure out, well, what is the angle? Well, then we're going to use the inverse tangent function. So the angle theta here is given by the inverse tangent of the ratio between our y velocity and our x velocity. Now, x and y components don't cross dimensions. Horizontal velocity does not affect the vertical acceleration of the ball. And then likewise, accelerations in the vertical dimensions do not affect the horizontal velocity of the object. And so here I got a short video that we can see that this actually is true. And so let's watch this. And so what's happening here is the ball on the left is going to drop straight down, and the ball on the right is going to shoot to the right. And notice they both hit at the same time. Even their bounces are identical. All right, now we don't have to watch him clean up. We'll just go ahead and move on. So how do we solve two-dimensional problems? Well, they're actually quite simple if you follow the steps and you break it down and think about it logically. The first thing you want to do is you want to break all of your vectors down into their x and y components. That's imperative. We use the sine and the cosine functions to do that. And then we're going to treat it just like two one-dimensional problems. In one case, in the x direction, there is no acceleration. And in the other case, in the y direction, there is an acceleration, and it's equal to negative 9.81 meters per second squared, or 9.81 meters per second squared down. And that's the free fall acceleration of gravity. Once we get to the end, we can reassemble the vectors to get our final velocity, our final total velocity. Or usually what we try and find is how far the object falls, or how far from the start does it actually move horizontally. And so we have to apply our kinematic equations in both dimensions. And so these are going to look a little bit different, but they're the same exact equations. Now in the x direction, it's actually quite simple. We call the delta x, or the change in the x position, we call that the range of the object. And so the range of the object is given by delta x equals the velocity in the x direction initial times the time. Because there is no acceleration, this is the only equation we have. We don't have to worry about coming up with other equations or rearranging. This is it. Okay. Now to find the vertical quantities. Now these are where they get a little bit tricky. And these are the same exact equations that we've had for vertical motion or free-falling motion, except now we have to take into account that we have a y component. So our velocity in the y direction final is going to equal our velocity in the y direction initial plus the free fall acceleration of gravity, 9.81 meters per second squared down, times our time. The second equation is the velocity in the y direction final squared is going to equal the velocity in the y direction initial squared plus 2 times the acceleration of gravity times our change in our vertical position. All right, and then our change in our vertical position equals our initial velocity in the y direction times our time plus 1/2 times the free fall acceleration of gravity times time squared. Now, the most common use of these equations is you will use this bottom equation on the vertical side, on the y side, to find out our time. Because this is going to tell us how long the object is undergoing projectile motion, or how long the object is in the air. Once we solve for time, well, we can solve for our velocity, our initial velocity in the x direction, quite simple, just by the velocity they give us. And we know our time, we can figure out the range, or how far the ball goes. We will use this even in real life in class. When we do a lab, we'll do a lab called the projectile launcher lab, where we'll actually shoot a ball out of a projectile launcher and try and hit a target, where we're looking for this range given a change in our y and our initial velocity. All right, so that's all I have. Some example problems are to follow, but right now, that is the gist of two-dimensional motion or projectile motion.